heads, tails. Sorry. Tails, tails, head. And then tails, tails, tails. So what you just did is you created the sample space. And inside of this sample space is how many items? How many events occur in the sample space? How many events are here? There's 8 total events. Everybody got that? But what am I actually interested in for this particular problem? The number of heads, right? So we're going to make a table where the first thing we're going to do is it says, what is the random variable x defined as? Well, x is equal to the number of heads. And here's how we define a random variable. We use a capital letter X and we say it's equal to something. In this case, equal to the number of heads. To make the table looks like this. You're going to tell me what the possible x values are, and then you're going to give me the probability for each one of those x values. So you're going to tell me what the possible x values are, and you're going to give me a probability for each one of those x values. Well, x stands for what again? Number of heads. So what are the possible x values? What's the minimum number of heads you can get when you flip 3 coins? 0. Why 0? That's the case what? Tails, 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 where you get what? No heads, right? So here's what you're going to do. Starting with the smallest number, you get 0 heads. Then you can get 1 head, 2 head. What's the maximum amount you can get? 3 heads. Everybody got that? Now go through your table and do this. How many times do you get 1 head in this table? Or do you get 0 heads in this table? 0 heads you get how many times? Once, when it's tails, tails, tails. That's 1 out of how many? 1 out of 8. Why is it 1 out of 8?
Because it's 8.
8 total events, you only had 1 that came up with no heads, right? How many times do you get 1 head in this? Well, you get it here, here, and you get it here. Do y'all see why?
Yes.
There's 1 head inside of there. Everybody got that?
Yes.
So how many times does that occur? 3 out of 8. How many times do you get 2 heads? 1, 2, 3 again, right? So that's what? 3 eighths again. And then the last one is 1 head, which is 1 out of 8, right? Now the question is this: is this a valid distribution? Yes or no?
Yes.
How do you test it? How do you tell if it's valid?
Because it equals to 1.
It adds up to 1, right? And all the probabilities are less than 1, but they're greater than 0. So no negative probabilities. They're all less than 1, but they all add to 1. Everybody got that? So this is the distribution. This is what we call the the discrete probability distribution. When you make this table, you're making a discrete probability distribution. Everybody got that? Now, we're going to use this table to answer these questions here. And so the first question says this: what is the probability of no heads? When you write it, I want you to get in the habit of writing statements. Here's how you write the statement for this. The probability of no heads means that x is equal to what? Right there. X equals 0. That's what that's asking me for, right? And if we read this based off what we defined x as, what does x stand for again? The number of heads. What does this say? The number of heads is equal to
0.
So what is the probability of no heads? That's this right here. We said that's equal to what? 1/8. Look at the next one. What is the probability you get 2 or more heads? What does it mean to get 2 or more heads in terms of this problem? You can get 2 or 3. What does the word or mean? What does that word or mean? That means to add. Good. So you can do this. The probability that x equals 2 plus the probability that x equals 3. What's a quicker way to do this? What's a quicker way to write this, or a more efficient way to write this? That's the answer. Well, what's a more efficient way to write 2 or more? The probability that x is what? Use a symbol.
2 plus 3.
Use a symbol.
Dash.
Greater than or equal to. Good. Why greater than or equal to?
Because it can be 2.
Well, it can be 2 actually. That means it can be 2 or it can be 3. In this case, greater than or equal to means 2 or 3, right? That's equal to 2 is 3/8. And 3 is 1/8, right? 3/8 plus 1/8 is
4/8.
4/8.
It's also 1/2.
Or 1/2. Now, we don't want to reduce this. Why? But when I look at this, what does this 8 really mean right here? There's 8 events in there, and how many events were in favor or for this right here?
2.
Or how many were in favor of it? 4. 4. We see that there's 4 events that are in favor of what we're looking at. Everybody understand that? If we reduce this to 1 over 2, what would we know? Or what could we not tell?
We would think there was only 2.
There was only 2 events, only one of them was in favor. Does everybody understand that?
Yeah.
So don't reduce in probability. Look at the next one. What's the probability you get at most 1 head? What does at most 1 head mean?
That means that you get 1 head
Or
more.
no, at most. At most means what?
Oh, 1 or none.
So in this case, at most would be what? The probability of at most 1 head would be x equals 0 plus the probability that x is equal to 1. A quicker way to say that is to say the probability of x is what?
Greater than or equal to.
Try it again. Greater than or equal to be 1, 2, 3. Less than or equal, because that means what? Less than or equal to 1 means what numbers?
It's gonna be less than 1.
So it'll be 1 or 0, which is what we're looking. 1 or less, which is those two. So you get 1a plus 3a's, which is 4a's.
5.
Sarah travels along a main road in Houston. In doing so, she travels through 3 intersections with traffic lights over a stretch of 2 miles. The probability that Sarah will have to stop at any intersection over this stretch of travel because of a red light is 40%. Let X be the number of red lights she encounters. So we're going to make a Trina table for this situation, all right? And it works like this. Either you're going to stop at the intersection or you're going to go through it. Everybody got that? The probability you stop at it because it's red is what? 40%. So that means that it's green or whatever. The probability that you don't stop is going to be what? 60%. 40% you're going to stop, or 60% you won't stop, right? So you go through your first intersection. How's that set up? Well, it can either be red or it can be green, right? Everybody got that? So next intersection, it can be what? Red or green for both of them, right? And then the third intersection, it can be red or green again. Now, we know the probability that it is red is what? 0.4, right? And you could go through this entire table, and wherever you see red, what would you put? 0.4, everybody got that? And wherever you see green, what would you put? 0.6. And you can do it for the entire table. Now, here's what we're actually interested in, though. X is equal to what? What did it define X as this time? Let X be the number of red lights she encounters, right? So for this one, I'm going to let, if X is that, here's what I want to do. I want to make a table where, what's the minimum amount of red lights she can encounter? 0, which means she did what? She got all green. What's the maximum number she can encounter? Which means she had to stop at every light. Everybody understand that? So our table looks like this when we set it up then. You have an X and you have a probability of X.
So for these 12, you have to do 3 events each time?
Not each time, but for these particular problems, you're doing 3, because how many intersections did you go through? She went through 3 intersections, yeah. So that's 2, and that's 3, right? Now, here's what we need to calculate. What is the probability she goes through 0 red lights? Well, what branch is that on for us? What branch is 0 red lights on for us? The green branch. Everybody see that? Green, green, green. Y'all got that? That's when she goes to 0 red lights, or when she doesn't stop at all. Everybody understand that? How do I calculate the probability for green, green, green? What is the probability of being green? 60%. So this is 60%, this is 60%, and this is 60%. We're going to assume that they're independent, because one red light shouldn't affect another red light, right?
Right.
If they're independent, what can you do to their probabilities? What can you do to probabilities when they're independent?
Multiply.
Multiply. So what do we do to those 0.6s? multiply. So we're going to do this. So we're going to do 0.6, right? 0.6 times 0.6 times 0.6. What does that 0.6 times 0.6 times 0.6 actually mean?
0.6 to the third.
What does that mean, though? In terms of this problem, what does it mean? It means she went through what?
3 green lights.
3 green lights. Everybody understand that? So 0.6 to the third is equal to 0.216, which means she encountered how many red lights?
3.
No, how many red lights?
Oh, none.
No red lights. So where's that going to go on our table then? That's going to go for 0, right? So our 0 is going to be equal to 0.216. How do you calculate one green light? One red light. What would you do now? 0.60 times 0.60 times what? 0.4. Everybody understand why? If you're doing one green light, that's what? One green light is 0.6. One red light. I'm sorry, one red light. You're doing one red light, that's what? 0.4. The other two lights have to be what then?
0.6.
So that's 0.4 times 0.6 times 0.6. And that's equal to 0.144, right? But look on this table. How many times does that actually occur when she goes through one red and two greens? Well, one red and two greens. If you look here, you have red, green, green on this branch right here. Do y'all see it? Red, green, green. Do y'all see that?
Yeah.
That's one time. Everybody see that? You also have it green, red, green.
Right there.
This is also a second time. Everybody got that?
Yes.
You also have it where green, green, red, which is, how many times does she actually go through that then? 3 times. Everybody understand that? So what do you need to do to that 0.144?
Multiply times 3.
Multiply it by 3. So 0.144 times 3. And you get this. So she stops at one red light at what probability? 0.432. What'll make this easier for you is to do like you did in the last problem up here. When you did this problem up here and you wrote all these out right here, you're going to do the exact same thing for this problem. So if you write them out, here's what you're going to get. You get green, 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 which means they were all what? They were all green. Then if you follow your branches, you're going to get a branch that says red, 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 which means they were all red. Keep following the branch. You get red, red, green, red, green, red, red, green, green. On the bottom branch, you get green, red, red, green.
Are you saying red or green?
Yeah, green, red, green, and then green, green, red. Everybody got that? So if I'm looking at just one, circle all the ones where you have one red in it. You have one red here, you have one red here, and you have one red there. So how many do we have that are just one red? 3. How many do you have that are 2 reds?
1, 2.
So you have 1, 2 reds here, 2 reds here, and how do I calculate 2 reds and a green?
0.4 times 0.6.
Good. 0.4 times 0.4 times 0.6, right? The 0.4 stand for what? So how many reds did you have to stop at? 2. So red, red, so it's 0.4 times 0.4 times 0.6, which is green. That equals 0.096. But you did that how many times?
3 times.
So multiply that by 3 and you get this. 0.288.
3 red is
Now how do I calculate the 3 red case?
1.
0.4 times 0.4 times 0.4, and it's equal to what? 0.064. Does everybody see that? And so here's the actual table you're going to create from then. Here's how we created that table. And now we can go and answer the questions. And the first question says this. What's the probability of being stopped by all 3 red lights? So how do you write that? The probability that x is equal to what?
3.
3. And that's equal to 0.064. Everybody got that?
Yes.
The next one says find the probability of having to stop at least one intersection. Let's just say at. So at least one, what does that mean? Probability of x is, what does at least 1 mean?
Oh,
Greater than or
equal to.
equal to 1. It's actually bigger than 1. So in this case it would be what? Either she stops at 1 red light, 2 red lights, or 3 red lights. So you could add up these 3 back here, right? But what would be the quicker thing to do? Who does it not include?
The first one.
So what can you do to find this?
Subtract.
Just subtract. So you could do 1 minus the probability that x is actually equal to 0. 1 minus the probability that x equals 0. Why 1?
Because they all equal.
They all have to add up to what number? 1. We're going to take these away from 1 and we get what? 0.784. 0.784. If you add up all three of these, what are you? If you add up these three, what do you get? 0.784 as well. Next one says, what is the probability of having to stop at no more than 2 intersections? So no more than 2. What does that mean?
Less or greater.
So good. So that's x is less than or equal to 2, which would be these back this way, right?
So you just
What's the quicker way?
Subtract 1.
Subtract which one?
0.064.
Good. So subtract 1 from the 3 case, right? Which is 1 minus 0.064, which is 0.936. 0.936.